What's up, niggas? Let's learn about assembly today. Alright, so these are the topics we're going to be going over today. We're going to do a basic, simple hello world to print SCD out. We're going to be talking about the system call table configuration for the x86 underscore 64 architecture. We're going to be discussing calling conventions, what assembly language is, the system via ABI, aka the application binary interface for basically Linux and GNU operating systems. We're going to be talking about assemblers, linkers, and how to actually execute the executable we will be creating today. Alright. First things first, we're going to go into a file with a .asm extension. Okay, first things first, we're going to set a entry point for the GNU dynamic linker and loader. Now, later on, we'll go over what a linker is and what it looks like, how to use it, and how it works on a low level. But first things first, we're just going to create a very simple hello world. And then I'll go into explaining what exactly is going on here.
Stupid little fucking sussy baka.
And like I said, I'll be breaking this down later on once we go over more topics. Okay. So this should be our hello world. We're gonna go back into. Hold on, once.
Nano's better than Vim.
Having a little bit of complications here. Okay. So let's go over the system call table configuration. You might be, wondering what that means, what that is, how it works. So the way assembly language works is that you don't necessarily have functions in a shared object library that comes with the language, like more higher level languages like C and things like that. You don't have that. You work with system calls. System calls are a way to directly communicate with your kernel and get tasks done compared to function calls, which are different. That is delivered by your program compared to your kernel. So the system call table layout is different between x86 and x86 underscore 64. They have completely different calling convention tables, which I will actually link in the bio. You can actually go and look at this is called configurations. Next topic will be calling conventions. Calling conventions are how function parameters are stored. By functions, I mean like system calls. They're going to be your system call parameters that are stored inside of registers. Now, for the system v ABI, which is mainly Linux, which includes your file formatting executables, which would be ELF. It has your calling convention, has your auxiliary vectors. It has your environment variable information and such. We're not going to go too much into what ABIs are, but what you do need to know is how function parameters are stored. First argument, or first parameter, is not stored in RSI. I don't know why I did that. Stored in RDI. Second one stored in RSI. RDX. You will most likely not use RCX as the calling convention. You'll mainly use it as a loop. So, well, it is still a calling convention. It's still a standard calling convention, but you're not going to mainly use it as a calling convention. You're going to mainly use it as a loop for things like control structure programming. But we're not going to worry about that right now. You have R8 as your 5th, R9 as your 6th. And, it goes on and on and on up until route 7 or 8. And then the rest are stored onto the stack. Okay, let's go over what assembly language is, right? So assembly language is the lowest readable format of programming to this date. Right behind it is machine code, which is it's considered you can read 2-bit binary by ones and zeros, but that's just a waste of fucking time. You can do it, but it gets very tedious. So that's why assembly language was introduced into programming. So to understand the correlation between assembly and other high-level languages is that when you have your compile languages like C, you're using GCC, CLang, whatever compiler you want to use, it'll compile it down to machine code, or not machine code, to assembly, and then it'll assemble it and link it with shared object libraries, which we will go into what linkers are in a little bit, and actually create an executable, a binary executable that we can therefore run. Already discussed what system ABI system ABI is assemblers. Okay, so assemblers and compilers relate only in the way to reforming our code into machine code, but other than that, they don't relate at all. Assemblers basically assemble your assembly code into an executable binary format, that file formatting being whatever operating system or architecture you're on. If we're on Linux using the system v ABI, it'll be in a ELF format. Well, I'm not ELF structuring and shit. You can go in. It's not very useful for learning assembly. That's just other low-level concepts that you'll worry about later on. You actually probably won't even have to worry about it in the first place. So that's basically a rundown of what assembly is, right? Now, as far as linkers go, I'm gonna draw a little. So we have our .asm file, right? We assemble it into an object file that gets linked with shared object dynamic library files. For you to be able to run your file, make it executable, you have to link it with dynamic and static libraries. That's the whole ideology behind a linker. It links library shared object files. And with dynamic linkers, you have PLT, GOT, you have DL runtime resolve, which will resolve symbols upon runtime, but we're not gonna get into that. That's for a whole different episode of me explaining GOT and PLT. We'll worry about that later. And now, as far as execution goes, you just assemble it, you link it, you execute it via doing this. As an input file .asm, file format being ELF64, so we're on the system v ABI and we're on Linux. We're gonna pip that output into an object file. Like I said, we're gonna link it using the dynamic linker that you can actually see here, ld.so. And it'll explain the dynamic linking and loading process. It'll talk about preloads, things like that we're not necessarily going to go over today because, for one, it'll take too long, and two, it's kind of useless because we're only just now getting to the basics of assembly. So we're going to link it. We're going to link that file. We're going to make it a binary. Okay, so let's go ahead and show that process off. So we're in an ASM. We have our assembly file right here. We're going to do our file format. We're going to do asm.o. We're going to link it. And we're going to run it. Oh, wait, hold on. Would you look at that? The reason we got a segmentation fault is due to the fact that we didn't actually exit the program using which we can actually do right here. But our code ran. Now, let me go ahead and break down each single line, right? So global start. We're using this for an entry point for one NASM and two the dynamic linker. We need that. We need that. Okay. Next is section.text. Sections in assembly are ways to define data that you want to use. So section.text would be your instructions. This is where your code's going to be. Section.data is where you're going to define initialized data, as you're seeing me do here. We have a quote-unquote variable. Variables don't necessarily really exist to assemblers in assembly, but at a higher level perspective, they do. So message defined by it's basically, this would be the same thing as, doing, these are comments in assembly, by the way, or little semicolons. This is the same thing as fucking doing this in your higher level languages. That's basically the same thing with a null termination, but we're not worried about that. And this is just the length, so it'd be the same thing as doing this. You're just defining the length for the parameters. So, move RAX1. RAX is a general purpose register, a general purpose scratch register that is going to be used for setting up system calls. It is going to be your structuring for system calls. So, remember how we referred to the Linux system call tables for Linux? You will notice syscall tables right here, or not for Linux, for x86_64. Alright, let's see if this source is good. See? Each number represents a system call. And we're doing one to write. See, first parameter would be the file descriptor, which would be stdout, which, one thing I forgot to mention, was file descriptors. 0 equals stdin, 1 equals stdout, 2 equals std. I'm not going to necessarily go into explanation, deep explanation between what these are, because if you have any sort of basic programming knowledge, you will know what these mean, or any sort of little low-level understanding. stdin is standard input. It reads from a file stream. stdout just prints to a file stream. stderr is the standard error, which is just a logging mechanism for your program, which we're not going to worry about. So, that's our file descriptor. The second parameter of the write function is the string you actually want to print to stdout, which we define right here, which is hello world, which is what we're defining. Second parameter. Third one being the length to the string, which we have done here. We can also do, other things we could do, like, for example, we can do Leah, RDX, dereference message. But that's a little bit more advanced. We'll learn about load effective memory address and basically point arithmetic in C or in assembly later on. That's for a whole different topic. So we're gonna do our length. So that's our third parameter. So we've completely set it up. So now we're gonna invoke the system call. Now this system call instruction will make a call to the kernel and it'll actually invoke our system call. Now for x86 assembly, it would be int 80 0x80 or int 80h, which is just the same thing as doing the first one. You'll learn about integers with D, octet, decimal, hex. You'll learn about that later. That's not really important for now. Ret basically returns control flow to RSP, which would be considered the top of the stack, which is what we're doing. We'll learn about things like enter and leave for actual stack frame programming and actual structure programming in a later video. But I do want to quickly talk about the BSS section, which is for uninitialized data. So it would be pseudocode for C would be like char buffer fucking 64. This would be the same thing as this, reserved by 64 hex. Same thing. It's the same exact thing. It's reserving data. It's for uninitialized data, meaning it hasn't been initialized. So that is a basic hello world in assembly. So topics we went over today would be, if I can type, topics we went over today with hello world, subcall table configuration, architecture, calling conventions, system VABI, assemblers, linkers, and execution on how to actually assemble and link your assembly files. Now, this completely justifies our basic topic and basic explanation of assembly.